Sudah, Pak.
Oke, terima kasih. Oke, selamat pagi semua. Mohon maaf saya telat ya, saya lagi di perjalanan sebentar. Jadi apa namanya, hari ini kita belajar tentang electromagnetic wave. Oh, sorry, I'm sorry. So today we will discuss about electromagnetic waves. This is the waves which propagates. It doesn't propagate through the medium. It doesn't need the medium to propagate the waves. Okay, so last week and the last 2 weeks we have discussed about a mechanic wave where these waves propagate through the medium. Okay, they can only propagate through medium. Okay, if there is no medium, then they cannot propagate. Okay, so this is the special case. I mean, another type of wave which can propagate without medium. This is called electromagnetic waves. Okay, this electromagnetic wave is the implication of the wave equation coming from Maxwell equation. Okay, so how do you recognize this picture? Do you know anything about this picture? Hello? Anyone? Anyone recognize with this picture? Know about this picture?
Is it a nebula, sir?
Yeah, exactly. This is the nebula. Okay. This is the nebula, okay? So this picture is the this image is is already somehow using computer. They what is it? I forgot in English. Somehow they're using so usually we have the astronomical data and then we use computer to compile this data. Yes, so we get this one. If you have already heard about the black hole picture, this black hole picture is around 1 terabyte data, which is also compiled by the computer. Okay, this is using supercomputer to compile this data, then we get this picture. Okay, it's similar to from our eyes. Okay, it's similar from our eyes. Our eyes, somehow there is a mechanism. For example, in light, for example, light that passing through our eyes, they will be compiled by our it's a brain also, but will compile through the eyes. Okay, somehow this eyes is the sensor of this light. Okay, to see something in front of us, for example. So this somehow usually this picture compiled by the computer, the data usually in radio wavelength, not in light wavelength. Okay, as we have discussed or mentioned just now, this wave equation called electromagnetic equation is the implication of Maxwell equations. Okay, so Maxwell equation, we have this one, 34.1 and 34.3. This is the first one is the Gauss law of electric interaction. Yeah. And the second one is the magnetic interaction. Okay, so in the first one implies that we have electric monopole, while the minimum object of the magnetic from the distribution of the magnetic field in the volume is dipole. There is no magnetic monopole. Okay, only magnetic dipole, at least so far in room temperature today. Okay, and the third and the fourth one you know this, the third one is the Faraday lens, yeah, Faraday lens equation, okay? And the fourth one is the Ampere-Maxwell equation. So basically Maxwell add these last two, the last term in order to satisfy some, we call it the continuum equation, okay? So if we consider the vacuum Maxwell equation, vacuum means there is no source, okay? There is no source, it means this Q here equal to 0, and also this one equal to 0. This I here, there is no current source here. There is no current source here, okay? So this fourth equation will implies this electromagnetic wave equation. So this wave, I will not write the wave equation. It's similar to, yeah, it's wave equation. It's similar to the mechanic wave equation. It's similar, but it's a vector, okay? Let me write it to you. Okay, I will write. So waves. So wave equation. So we get, for example, this this is a wave equation. This C here is a function of x and t. This we could write this x plus minus vt, okay? So what we have last week, this C here is equal to, let's say this m, the amplitude, and this, there is a sinus, kx minus plus minus omega t, okay? This k here is 2 pi over lambda, and omega is 2 pi f. Okay? This is mechanic wave. So electromagnetic wave so we just replace this C by, for example, I took E, the vector, this is the electric field, okay? This electric field, we call it this E0 or EM. The amplitude, for example, is minus sinus kx plus minus omega t. Okay? So x here is the direction of propagation. Yes. X is the direction of propagation. And this is the amplitude. Okay. For transversal waves, sorry. It means that, for example, EM vector I take M at the direction of y-axis. Okay. What is the unit of electric field? I think it's Newton per coulomb. Yeah? This one. Okay, is there any question? Any question? Any question? Hello, any question? Anyone?
Not at the moment, sir.
Okay. 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 Let's continue. Okay. So basically, we have to solve this Maxwell equation. Okay. This 34.6, this equation coming from Faraday-Lenz equation, which is the third one here. Okay. And the second one here is coming from the Ampere equation. Okay, this VE is the flux of the electric field flux. Okay, electric flux. Yeah, electric fluxes. Okay, electric fluxes and also magnetic fluxes. This VE is electric fluxes, while VB usually I refer to magnetic fluxes. This is electric fluxes, and this is magnetic fluxes, phi B and phi E. Okay. So using these two equations, we could what is it? After some computation, we arrive to the equation 34.8. Okay. For E. Okay. And for B, you could use this equation 34.7. We differentiate it, and then using the above equation, we get also this one. So it means that whether you use E or B as the function of electromagnetic field, electromagnetic waves, okay, it is equivalent. Okay, it is the same. Okay, so somehow this electric field is connected by B. Okay, somehow there is a relation between E and B. This relation can be found using these two equations. Okay, these two equations. We will see about that. Okay, so we conclude from this equation. This basically this 34.8 and the 34.9 is the waves equation. This quantity, we call it 1 over c squared, which is the speed of the electromagnetic waves. Just we call it c. C is the speed of electromagnetic waves in vacuum. In vacuum, okay? Vacuum means there is no matter. Vacuum. There is, yes, it's empty. There is no thing there in there. Okay, this C here is 1 over square root mu 0 epsilon 0. Okay, where mu 0 is the magnetic permeability, while epsilon 0 is the permittivity, electric permittivity, vacuum electric permittivity in vacuum. Okay, is there any question? Any question? No. Okay, let's discuss about the function, the wave function. So for example, for simplicity in our lecture, in our course, in elementary physics, okay, this E usually we take the form to be harmonic. It means that we could choose whether we use sinus function or cosinus function. Okay, it's the same. But if you choose E to be the function of cosinus, for example, this E equal E max is cos kx minus omega t. So omega t. So it should be the B also have the same function. This is also cosinus kx minus omega t. Okay. So this is, I think this is the simple principle. Whether you first, for example, if you choose the electric field to be the function of cosinus, then the magnetic field also follows, also cosinus. Okay. And also if you use this B to be cosinus, and this E it should be also cosinus. Okay. So this K is the number of wave. Okay, this is related to K 2 pi over lambda, and omega is the angular frequency. So this omega over K, we get this C, okay, which is the speed of the electromagnetic wave in vacuum. Okay, so the approximate number this about C is 3.3 times 10 to 8 meter per second. Okay, you can imagine that with this speed, the electromagnetic wave can move around the Earth around 7 times. Okay, and it could also travel from, for example, the sun to the Earth in 80 minutes. Okay, we know that the distance from the sun to the Earth is around 150,000 kilometer. I think, yeah, maybe above. Okay. So how to find the relation between Mx and Bmx? Okay. So first we derive partially this E with respect to this X. Okay. This E. Okay, we get this one. And while B, we derive it partially with respect to T. Okay, we get this one. So using this equation, dou E over dou X equal minus dou B over dou T. Okay, this partial. Okay. So we get this one equal minus this one. So it means that we get K A max equal to omega B max. Okay. So we get this relation. So it means that E max over B max is equal to C. Okay. So E max equal to C times B max. Okay. Is there any question? Any question? Any question? Any question?
No, sir.
No, sir. Okay. Yeah. Wait a moment. Yeah. Okay, let us continue. So we get, for example, this picture. For example, we have. So from the function, we knew that this this electromagnetic wave propagate through x-axis. Okay, this one. So E here, yeah, E here. Which one? E here, okay. So because we have this transversal and planar waves, so it should be the oscillation of E, okay, is perpendicular to the x-axis. Okay, it should be, for example, we take this oscillation direction of the electric field to be in y-axis. Okay, while this E and B is related by crossing. Crossing means, yeah, this one. By crossing, it should be uh, the B field, this magnetic field, is also perpendicular with perpendicular to E and also the propagation direction. So it should be the oscillation, the magnetic oscillation direction should be in z-axis. Okay. So this is the diagram. Yeah. For example, this is y and z. Okay. We have this picture. Okay. This one. And then they become bigger also. This E become bigger. Yeah. Then also B. Okay. And then they become smaller, and then 0, and then they have different phase, negative phase. This is maximum, and then become smaller, and then smaller. Okay, and this is the picture like this. So the picture, so this kind of electromagnetic waves, it's somehow we call it this polarized. Yeah? Polarized electromagnetic waves. Why we call it polarized? Because we have only one direction of oscillation, which is in the y direction. For example, in E, while in B, in Z direction. So somehow this direction, the direction of the oscillation is fixed. Yeah? They cannot change. They fix through the time. Okay. Is there any question? Somehow it's not clear what I mean about or I'm talking about. Is there any question? Question? No. Okay, let's continue. So for example, this is the example. A sinusoidal electromagnetic wave of frequency 40 megahertz travels in free space, it means vacuum, in x direction as the figure 34.4. Okay, this one. Determine the wavelength and the period of the waves. Okay. So the wavelength, it means that C over F, we have this 3 times 10 to the 8 over this frequency. We get the wavelength is 7.5 meter. Okay, and the period is 1 over half. Sorry, T is 1 over F, sorry. It should be 2.5 10 to the minus S second, okay? Okay. B, at some point and at some instant, the electric field has its maximum value, sorry, 750 Newton per coulomb. Long y-axis, calculate the magnitude and the direction of magnetic field at this position and time. Okay, so they have the same time and position because this is the amplitude. It's always the same, yeah, in this case. Okay, this Bmax is equal to Mx over C. Okay, this Mx here, long y here is 750 Newton per coulomb. Okay, divided by the C, we get the max, the amplitude of the magnetic field, yeah, is 2.5 times 10 to the minus 6 Tesla. Okay, is there any question? This is the example. Okay, this is the formal derivation of this formal derivation of this 34. Yeah, 34.6 and 34.7. Yeah, this. So okay, don't you have any question now? Okay. So okay, the energy carried by electromagnetic waves. Okay. So as we know, this wave phenomenon is the energy the wave phenomenon is somehow they propagate also the energy. Okay, so this energy, we call it this energy flow, described by the Poynting factor. Poynting is the name of a person. I don't know the complete name, but Poynting is the name of the factor who proposed this quantity, this vector quantity. We call it Poynting factor. This Poynting factor describe the flow, the rate flow of the energy of electromagnetic field. Okay, this S here equals to 1 over mu 0 E cross B. Okay, so as I have already mentioned before, I think, yeah, the energy density for volume. Energy density per volume. Okay, we call it this little u is equal to epsilon 0 over 2 e squared plus 1 over 2 mu 0 b squared. I think we have discussed it, okay? Yeah, this one. So this is for capacitor, for example. This is for inductor. But in our case, we have both electric and magnetic field. So this is the general formula for energy density per volume for electromagnetic waves. Okay. The flow, the energy flow, sorry. So the energy flow is described by, we call it, yeah, this Poynting factor. Okay. So this satisfies, we call it the continuous equation of motion. This one. Okay. We call it this continuous equation. Continuity, I think. Sorry. Continuity equation. Continuity equation. Okay. Okay, let's say to this one. Okay, because E and B is perpendicular to each other, if we compute the magnitude of this factor, this Poynting factor, we get this 34.20. Okay, because B, there is a relation between B and E in this case, we get this S here equals to A squared over mu 0 C. Okay. Okay, because the function is the function in general, it depends on x and t. So we have to make this quantity to be average. We have to average this function, okay, for fixed point. So this point, usually we get this x equal to 0, okay, for arbitrary t. For arbitrary time, okay. So if we compute the average of this s, we get this 34.20. And it is related to, we call it intensity, I. Okay, this is the intensity, I, the intensity. So the intensity, for example, for the sounds is related to the level of hearing, okay? The loudness, the loudness level, for the sound. For light, it's related to the brightness level, okay, this I. Basically, it is somehow related to energy, okay, energy per, not energy, power over an area, okay. Is there any question here again? If not, I continue. Okay, so this is the I here, the intensity of the waves, okay. So you see that because S is E cross B, while E and B is orthogonal to each other. So it should be the direction of S is equal to or parallel to the direction of propagation of the waves, okay? So this one in figure 34.7. Okay, so we get that the magnetic energy density, we get this one is equal, and also, sorry, this EB, UB is equal to UE, okay? So somehow, because this is the same, it should be twice. So we have epsilon 0 E squared or B squared over mu 0. Okay, so we get, after some computation, we get that this I here is equal to the average of the magnitude of pointing vector. And we get this is equal to the C times the average of the energy density for volume of electromagnetic waves. Is there any question? Hello? Any question? And if there is no question, I will continue. Any question? Okay. No.
No, sir.
Okay. Okay. What is it again? So this is this example. For example, fields on the page. Estimate the maximum magnitudes of electric field and magnetic field of the light that is incident on this page because the visible light coming from your desk lamp. Treat the bulb as a point source of magnetic field radiation that is 5% efficient at transforming energy coming in by electrical transmission to energy leaving by the visible light. Okay, so this is the intensity as mentioned before is related to the power over an area. So an area we choose as the sphere, okay? So because this P average, so because this I here equals to this one, okay? So this Emax here equal to, well, just a moment. It's not the 3 watt, it's not state in the problem here. So in the solution, okay. So approximately, for example, we have this 60 watt light bulb. Its output is 5% efficiency is approximately 3 watt, okay, by visible light. Okay. So this Emax here is square root over mu 0 C P average over 2 pi r squared. Okay, the reasonable distance from the bulb to the page, yeah, it's around, okay, this is, you choose this around 30 centimeter, okay. Then we get this Emax here is 45, around 45 volt over volt per meter. And Bmax here, the amplitude is around 1.5 times 10 to the minus 7 Tesla. Is there any question for this example? No question. Okay, let's continue. Just a moment, yeah. Any question? No. Okay, we continue. So we discuss about this, we call it momentum and radiation pressure, okay? This momentum defined as P equals to U, big capital U over C, okay? U over C, okay? And also there is a pressure, okay? Pressure, the definition of pressure is defined as F over A. F is the force, okay? And this force is dP over dt. Okay, so we insert this expression 34.24 to this one, we get this equation. So we conclude that the pressure caused by the light is equal to S over C. Okay. Okay. Do we have to discuss it again? Okay. Let's see. Okay, this one. I think this one is a good question. Okay, as noted in the preceding example, the sun delivers about 1,000 watt per meter squared of energy to the Earth's surface via electromagnetic radiation. Calculate the total power of that is incident on the roof of dimension 8 meter times 20 meter. Okay, this S average is equal to 1,000 watt per meter squared and at the roof of this area. So we get this P average is 1.6 times 10 to 5 watt. Okay. And B, also we've determined the radiation pressure and the radiation force exerted on the roof. Assume that the roof covering is a perfect absorber. Okay. Okay, we have this as average 1,000 watt per meter squared. Okay. We get this radiation pressure, the average of radiation pressure is S average over C. Okay. So we get that this pressure, it should be 1,000 over 3 times 10 to the 8. Okay, so we get this 3.333 times 10 to the minus 6 N per meter squared. Okay. If we, so this is 160 meters squared, okay? So the pressure exerted on the roof caused by the radiation pressure is this one. It's very small, yeah? It's very small. Compared to what we have calculated in the elementary physics 1, yeah, last semester. Any question? No, okay. So this is basically, so I will discuss it shortly. This is the production of electromagnetic wave by an antenna. So basically an antenna is like this. We have this somehow, there is a charge here, which is the alternating current. Okay, there is a negative and positive road, for example, yeah. And this is the source of this weak alternating current, okay. So we get that there is a B out here and B in here, okay. So this is B out and B in here, and also this orange line here is the electric field, yeah. So this is inside and this is outside. Sorry, this is outside and this is inside. So inside the page and this is outside the page, okay. It's like a dipole here, this antenna. But we have the magnetic field component and electric field component. So the spectrum of electromagnetic fields. Okay, we will discuss this one. So the electromagnetic field, the spectrum, it usually based on the frequency or the wavelength equivalently, okay? So for example, based on the wavelength, we have these radio waves and the wavelength range between 10 to the 4 until to 10 to the 4 meter until 0.1 meter, okay? So this is the low frequency and this is the high frequency, this 0.1 meter, okay? So radio waves, as we know the name, this radio waves is used for telecommunication, yeah, radio, okay, like handphone, everything, also, yeah, television and everything. Yeah, it's related to electromagnetic telecommunication electric device like phone, handphone, laptop, etc. Radio also, yeah. And the second one is the microwaves. Okay, this the wavelength is around 0.3 meter to 10 to the minus 4 meter. Okay, this is from low frequency to high frequency. Okay, so microwave usually we use for the radar, yeah, radar system to detect, for example, an object, massive object, for example, big object, and also we use for microwave. It's microwave somehow for heating food or meals, okay, in the household. Okay, this is also used wavelength. Sorry, this microwave. I mean, the wavelength around this wavelength. The third one is the next is the infrared waves. Yeah, okay. This is between 10 to the minus 3 meter to 7 times 10 to the minus 7 meter. Infrared waves. Yeah. So infrared means infra, below the red. So below visible light. Okay, below the light. Okay, it's usually used, for example, for photography and also physical therapy, or for example in military as this infrared telescope. Yeah, we could use also this infrared telescope. Yeah, because it captures these infrared waves. Yeah, the device and amplified to get this visible light. I mean, it's common to our eyes. So the next one is visible light. Okay, so the visible light usually, well, it is used by our eyes, yeah, to see things around us. Okay, this visible light. Yeah, this visible light wavelength. The wavelength. This is red. 7 times 10 to the minus 7. This red wavelength. And then to this highest frequency. This is the shortest wavelength in visible light. Okay, this is 4 times to minus 10 to minus 7 meter. This violet. Okay, and also the next one is ultraviolet. So ultra means above violet. Okay, so this between 4 times 10 to minus 7 to 6 times 10 to minus 10 meter. Okay, this ultraviolet. Okay. So this ultraviolet wave, we have a negative disadvantage. Okay, because it could cause cancer also, and also could well, somehow make our eyes blind. Yeah, if you see directly this light. Yeah, it's also coming. It is also coming from the sun. Yeah, this ultraviolet waves. Okay, and also could be used also for medical purposes, and also you sometimes or often see it in the bank. Okay, we could check the money, it could be fake or not. Okay, something like that. Yeah. This is the ultraviolet wave. So there is more application in this case. And then this X-ray, okay, X-ray, the wavelength between 10 to the minus 8 until 10 to the minus 12 meter. Okay, this X-ray is coming from the high energy electrons bombardment, upon bombarding the metal target or a target, yeah. So, or from Bremsstrahlung. Okay, Bremsstrahlung means that pengereman. Somehow when the electron moves or travels in high velocity, when it moves around the atoms or the nucleon or the nucleus of the core of the atom, okay, called nucleus, because the nucleus is positive, somehow it attract the electron, okay, so it cause the electron becomes slower. So because electrons become slower, then it has to emit the photon. Okay, so the photon is an X-ray wavelength. It's around 10 to the 8 meter to the 10 to minus 12 meter. Okay, so this one. So you know this X-ray have been used, for example, for medical purposes, like X-ray diagnostic, yeah, to X-ray photo, yeah, to see our inner side, we call it inner body, yeah, inner body, such as bone, organs, and so on. Okay. And the last one, which is the highest one, the highest energy of all, is gamma rays. Okay. This gamma rays is electromagnetic waves usually emitted by the radioactive nuclei, such as cobalt-60 and cesium-137, okay, or from the cosmic wavelength, cosmic rays. Okay, this cosmic ray usually coming from the supernova of the Death Star, not the Death Star from the Star Wars. No, the Death Star means the supernova from the star, yeah, and then usually the star after the supernova becomes white dwarf, yeah, and also become red giant star. Okay. Any question about the spectrum of electromagnetic waves? Any question? No question. Okay. Let's continue. Oh, okay. It's already finished this section. Is there any question? Any question? Okay. Beautiful picture, yeah? Okay. Any question? Hello, hello? Anyone's there? Hello? Any question?
No, sir.
No. Okay. Okay, tomorrow we will start at 12, yeah, as usual. Okay. At tomorrow, Tuesday. And then on Thursday, you have to collect your homework, okay? Module 6, yeah. I have uploaded in the Teams. And on Friday, we will have a tutorial session, okay, for module 6. And next week, on Monday, I will have a vaccination, second vaccination of coronavirus, yeah, COVID-19. It should be like previous one. If I late, I will inform you via Teams, maybe 30 minutes before, yeah, whether we have to cancel the lecture or we can continue the lecture on that day. Okay. Okay. I hope